A couple of other things that we'll be using when we're doing these types of calculations refer to the amount of water vapor that the air can actually hold. And the way that we quantify that is by the specific humidity and the relative humidity. So we'll begin by looking at the specific humidity. And this is given the symbol omega. And it is defined as being the water vapor mass to the dry air mass. So the mass of the water vapor to the mass of the dry air. Now what we're going to do, we're going to try to come up with an equation that enables us to calculate the specific humidity knowing the vapor pressure. And we're going to use the ideal gas equation for that. And we'll use the form with mass in it, not the number of moles as we saw earlier. So we can write specific humidity and if both of the components of the mixture are at the same temperature, and if they're both occupying the same volume, what we can write we get this expression here, and then the ratio of specific heats, that would be the value for air divided by the value for water vapor. So we get that, and in the numerator is the vapor pressure of the water vapor, and in the denominator is the pressure of the atmospheric air. So what we can do, we can continue on, and using the concept that the mixture pressure, the total pressure, will be a combination of the air and the contribution from the water vapor, we can rewrite the specific humidity in the following manner. And we get this equation here. Now, this is a useful relation. However, what we want to do is we want to look at the bounds by how much water we can actually add, or water vapor we can add, until we get to what we would call a saturation point. So we can keep adding water. And we can do this up until reaching what we call the saturated air point. And at that point, air will no longer take any more water vapor. And that would be the point where the condensation starts coming out of the air. So what we would like to be able to do is come up with a bound for the amount of humidity between completely dry air and completely saturated air. And in determining the completely saturated air, what we'll say is that the partial pressure due to the water vapor is equal to the saturation pressure that you would get out of the steam table at whatever temperature you are looking at, so the atmospheric temperature conditions. And so we can then write the specific humidity for saturated air where we've replaced the PV value, or the vapor pressure, by the value from the steam table for the saturated pressure, saturation pressure. So that gives us an upper bound in terms of how much water moisture we can add, and that would be kilograms of water moisture per kilogram of dry air is what we'd be looking at there. Another thing that we will be dealing with is referred to as being the relative humidity. And this is quite often what you'll see quoted in the evening news when they're talking about the weather conditions. And the symbol for relative humidity that we will use is phi. And phi is defined as the mass of moisture in the air divided by the maximum moisture that the air can hold. Again, we will use the ideal gas law. And what we get is a ratio of the pressures of the amount of the pressure associated with the moisture in the air divided by the max moisture, which we get off of the steam table. And that would be the saturation pressure at the given temperature. So we have a couple of different relationships, one for specific humidity and one for relative humidity. We can combine those together. And so those are two different equations that let you go between either the relative humidity or the specific humidity, knowing the saturation pressure, PG, and the atmospheric pressure that you would be dealing with. So that is relative humidity and specific humidity. The next thing that we'll take a look at is a way to compute enthalpy. Quite often we want enthalpy per kilogram of dry air, so that's what we'll look at next.